Hello. Today I thought we'd do a fun thing by approximating the Earth's mass using calculus and some numerical analysis. Well, in order to do that, I needed some data, so I got this data from the United States Geological Survey, the USGS, and the Earth is divided into layers. The innermost layer is called the inner core, and then comes a layer, the outer core, and then the lower mantle, then the upper mantle, and then the crust. In this column here, which I'm going to call rho sub n, is the distance from the center of the Earth, and it's in kilometers. So in other words, the inner core goes from 0 kilometers to 1,221 kilometers, and the outer core will go from 1,221 kilometers to 3,480 kilometers, and so on. And in the next column, each layer is given two densities. The density at the innermost radius and the density in the outer radius of each layer. And these are in units of grams per cubic centimeters. And I call the density of the inner radius of each layer d sub in, I referring to inner and n is the number of the layer. And I indicate the density of the outer radius as d sub on, O being for outer. And of course that's also in grams per cubic centimeters, and you can see that data here. Okay, well, armed with that, we're going to make a couple of assumptions. We're going to assume the Earth is a sphere, which it's not. It's kind of a ellipsoid of revolution, I think it's called. But in order to make this even possible, we're going to assume it's a sphere. And we're also going to assume the density of each layer is approximated by a linear interpolation, which it's not either, but it's just an approximation to make this thing easy. And we're also going to assume that the density only depends on the distance from the center of the Earth. I'm going to call that rho. So, in that regard, let's let d sub n of rho be the density function of the nth layer, where n is 1, 2, 3, 4, 5. And I rewrote all that data on the other page right here. So n is 1, 2, 3, 4, 5. So n refers to the inner core, 2 to the outer core, all the way down to 5 refers to the crust. And the rho sub n is the distance from the center of the innermost radius. So 0, 12, 21, 34, 80, and so on. And we have the d sub in and the d sub on there. Well, if we go back to high school, we have 2 points. We want to make a relationship between the density of the layer versus the distance from the Earth's center. So we want density versus rho in each case, for each n. And if we do our y equals mx plus b for those 2 points, the density of the inner layer and the inner radius and the density of the outer radius, we come up with this formula. So d sub n of rho will equal d sub in minus d sub on over rho sub n minus rho sub n plus 1 times rho, this is our linear factor, plus, this is our intercept, d sub on rho n minus d sub in rho n plus 1 over rho sub n minus rho sub n plus 1. We're going to call this first coefficient m sub n, and we're going to call the intercept b sub n. So m sub n is the slope of our little linear function for each n. Okay, well, I calculated all these offline, our m sub n's and b sub n's. And you notice that our densities were indicated by grams per cubic centimeters, but our distance from the Earth was, the units of that was kilometers. Of course, we want to have a consistent unit, otherwise we'll get erroneous results here. So I had to change all the rho sub n's to centimeters. And when I did that, our m sub n will be in grams per centimeters to the fourth, and our b sub n's will be grams per centimeters cubed. And that's why we get these big exponents here. So we can see we have our m sub n's are all negative, meaning the density gets smaller as rho gets bigger. So the Earth is most dense in the middle, in the center, and least dense on the crust. And I wrote our b sub n's, our intercepts. Okay, well, so far we have our distance function at each n. Now we're going to use our calculus. Well, we know from multivariable calculus that the mass of some sort of volume will equal the integral over the volume of the density of V dV, V being volume. Well, we can iterate that into a triple integral. Let's say the distance of x, y, z, for instance, of dz, dy, dx, with certain limits on our integral signs. But of course, we're using a sphere, so why not make it easy and use our spherical coordinates? We'll have the triple integral of d of rho phi theta times rho squared sine phi of d rho, d phi, d theta. Of course, this rho squared sine phi is our Jacobian. I have yet to put the limits here, but we're going to do that right now. So, the mass of our Earth, I guess we call the Earth V here, will equal the sum of each layer, of the mass of each layer. So we're going to write that as the sum as n goes from 1 to 5, 1 being the inner core and so on, and 5 is the crust. Okay, our theta limits will be 0 to 2 pi. We're just going to wrap around the entire Earth. Our phi limit will be from 0 to pi, from the North Pole to the South Pole, as we learned in multivariable calculus. And our rho limits will be rho sub n to rho sub n plus 1. We're going to calculate the mass of each layer one at a time that way. So the first one will be rho sub n to rho sub 2. That'll be determine the mass of the inner core and so on. And our d sub n of rho is our density function. And again, our rho squared sine phi is our Jacobian. Okay, well, let's put in that data so far. So we have the sum as n goes from 1 to 5, of the integral from 0 to 2 pi, the integral of 0 to pi, of the integral of rho sub n to rho sub n plus 1 of our density function, which we recall as m sub n rho plus b sub n. That's our density function. This is a rho here. It's kind of faded. Then our Jacobian, rho squared sine phi, and then d rho, d phi, d theta. Well, right away we can integrate out the sine phi and the theta integrals. When we do that, we get a 2 pi by integrating with respect to theta, because it's constant here, so we just go from 0 to 2 pi. And we integrate the sine phi. Well, that's very easy. That'll be the minus cosine phi from 0 to pi, and that'll give us another 2. So we have a 2 pi and a 2, and that'll bring us to 4 pi out here. We'll bring that on the outside. Then we still have the sum as n goes from 1 to 5. Now integrating what's left, which would be the rho squared sine times our density function, m sub n rho plus b sub n. Well, when we do that, of course, we get mn over 4 times rho to the 4th plus bn over 3 times rho cubed from rho n to rho n plus 1. Now, when we put these rho sub n's into this, we first have to convert to centimeters again, so we can avoid the erroneous results. And when we do that, I did that on Mathematica, we come with a figure of 6.04 times 10 to the 24th kilograms. And comparing that to our official figure from the USGS, which is 5.97219 times 10 to the 24th kilograms, that comes to a 1.17% error. So I think that's a very, very good approximation. And it was fun. We used a little bit of calculus here by integrating over the density function. And we did a little bit of numerical analysis by finding a linear interpolation of our density function. And it came out quite well, only a 1.17% error. And thank you very much for watching. If you liked this video, think about giving it a like. Thank you very much.